The story of our energy future might have started long ago in a place you might not expect. Rewind the clock. Go back to the 1960s. The world was looking to the stars while some of the brightest minds looked inward, into the heart of the atom. Oak Ridge National Laboratory, Tennessee, a team had a radical idea, a new kind of nuclear reactor, fundamentally different. They didn't want solid fuel rods. They wanted a liquid, a hot, glowing molten salt. The molten salt reactor experiment, a marvel of its time. It ran for several years, proving the idea was practical. The reactor hummed along, quietly efficient, hinting at a revolutionary path. Designed to be safer, designed to be more efficient, and designed to produce far less long-lived radioactive waste. Elegant simplicity, the reactor embodied it. It promised a future of nuclear energy that was abundant, clean, inherently safe. For a time, that future seemed within our grasp. But history doesn't follow a straight line. Now, more than half a century later, that lost dream is being reborn. So, what exactly is a molten salt reactor? Let's break it down. You don't need a PhD to get this. Think about a salt shaker. Imagine taking nuclear fuel and dissolving it into a special salt. Not table salt, a carefully chosen mixture. Fluoride salts, chloride salts that can withstand extreme heat and radiation. Heat that mixture until it melts into a clear, flowing liquid. That liquid becomes the fuel. It's the heart of the system. No solid fuel rods in a pool of water. Instead, a liquid that is both fuel and coolant. Like a car radiator, but huge. A pump circulates hot, radioactive salt through a core. In the core, a nuclear chain reaction happens. Atoms split and release huge energy. The hot salt flows into a heat exchanger. Heat transfers to a second, non-radioactive salt loop. That loop can boil water, create steam, spin a turbine to generate electricity. The system is continuous and flowing. You can add new fuel and remove the ash while it runs. The original molten salt reactor experiment at Oak Ridge was a stunning success from a scientific standpoint. It proved the concept worked. It demonstrated stability. It showed that the materials could handle the harsh environment. So why did we abandon it? As with many great leaps in human history, the answer isn't about science or engineering, it's about people, priorities, politics. In the context of the Cold War, the United States was in a race. The primary driver for nuclear development was military superiority, not civilian energy. The U.S. Navy had a powerful voice. It needed reactors for submarines and aircraft carriers. Light water reactors fit that need. They were compact, powerful, and maturing quickly. The light water cycle also produced plutonium, useful for weapons. Molten salt reactors, especially thorium designs, did not produce plutonium as effectively. They were meant for peaceful, efficient power. Industry momentum mattered. Fuel plants, waste storage, regulations were built for light water. Switching meant colossal investment. It was labeled disruptive and too expensive. So in 1973, the program's funding was cut. Scientists were reassigned. Research was archived. The reactor was left to grow cold. But history loops back. Today, priorities have changed. The Cold War is over. Climate is the threat. Suddenly, the old drawbacks look like strengths. Inherent safety, fuel efficiency, minimal long-lived waste. Fast forward to today. The torch that was extinguished at Oak Ridge has been relit with modern engineering and a fresh perspective. Chinese scientists and engineers, with significant government backing, have redesigned the molten salt reactor from the ground up. They studied the old plans, learned from the original experiment's successes and challenges, applied decades of advances in material science, computer modeling, manufacturing. The result is a prototype that's a significant leap forward. Their goals: smaller, inherently safer, more economically viable. One major change: physical size. The Chinese prototype is remarkably compact, a small, modular unit designed to be built in a factory, transported to its location. This approach slashes construction time and cost. Instead of decade-long builds, these reactors can be deployed faster and cheaper, from remote industrial sites to cities. A move from one-size-fits-all to flexible, scalable energy. Engineers amplified passive safety. In an emergency, gravity does the work. A frozen salt plug sits at the core's bottom, kept solid by cooling. If power cuts out, the plug melts and the liquid fuel drains into underground storage tanks. Those tanks halt the reaction and let heat dissipate into the earth naturally. No human intervention. Just physics. A key part of this story isn't just the reactor itself, but what you put inside it. The Chinese prototype, like the visionaries at Oak Ridge before them, is designed to run on a different fuel, thorium. Uranium has dominated for 80 years, but thorium is a fascinating alternative with big advantages. Thorium is far more abundant, about as common as lead. Countries with little uranium often have lots of thorium. India, China. Thorium isn't fissile, it needs a nudge. A small amount of fissile material like uranium-235 gets things started. Thorium absorbs neutrons and becomes uranium-233. U-233 then fissions, releasing energy and neutrons, converting more thorium into fuel. The reactor breeds its own fuel. That makes it extremely efficient. Nearly all potential energy is extractable. Result: far less waste. Some experts say waste volume could drop by a factor of 1,000. And the waste produced is different. Far fewer transuranics, like plutonium, americium. Thorium cycle waste decays to safer levels in a few hundred years, not millennia. It produces very little plutonium, and U-233 is contaminated, making weaponization impractical. Abundance, efficiency, safety. Section 6. The moment of truth. A stable fire. For any new technology, there comes a moment when theory must become reality. After years of design, simulation, and construction in the Gobi Desert. The goal: initiate a nuclear chain reaction and maintain it in a stable, controlled manner, like lighting a fire and keeping it steady. This milestone would validate decades of work and signal operational viability. In late 2021, the team achieved their goal. The prototype thorium molten salt reactor sustained a chain reaction. The liquid fuel, a glowing mixture, fluoride salts, dissolved thorium, began to fission. Neutrons split atoms, releasing energy and more neutrons, which split more atoms. The system worked. Pumps circulated the hot liquid. Heat exchangers transferred the energy. Most importantly, the reaction was stable. The team demonstrated precise control, raising its power output, lowering its power output as needed. Not a fleeting experiment, a controllable, continuous nuclear process in a completely new type of machine. Early results confirmed computer models. Passive safety behaved as expected. Materials held up under intense heat and radiation. This operational proof is a stepping stone toward commercialization. A reactor that runs on liquid salt and thorium is no longer a dream, it's a reality. To truly appreciate the leap forward, we need to compare molten salt reactors to the workhorse, the light water reactor. For over 60 years, light water reactors have been dominant. They are powerful, they are reliable, but they come with inherent challenges. A light water reactor is a giant, high-pressure machine using solid uranium fuel rods bundled inside a massive steel vessel filled with water. Water removes heat and sustains the chain reaction. The key word is pressure. To keep water from boiling at high temperatures, it must be kept around 150 times atmospheric pressure, a celestial pressure cooker. That demands huge, expensive structures to prevent release of radioactive steam. A complex web of high-powered pumps and emergency cooling systems tries to stop fuel rods from overheating. As we learned at Fukushima, safety depends on active management of immense pressure. Now, the molten salt reactor, a completely different beast. It operates near atmospheric pressure. The liquid salt doesn't boil until around 1,400 degrees Celsius, far above operating temperature. This eliminates the primary hazard of LWRs. No high pressure pushing radioactive materials out, no massive containment dome. The need for emergency pumps is gone. Safety is passive, gravity and natural heat dissipation. Operating pressure and fuel form change everything. Cost, safety, complexity. This isn't incremental. It's a paradigm shift. When people hear the words nuclear power, their minds often jump to two big concerns: the risk of a catastrophic accident like a meltdown, and the problem of long-term radioactive waste. These are legitimate concerns. The beauty of the molten salt reactor is that it addresses both at a fundamental level. A meltdown happens when solid rods overheat and melt. In a molten salt reactor, the fuel is already molten. It can't melt down. In a total loss of power, a frozen salt plug melts, and the liquid fuel drains by gravity into passively cooled tanks. The reaction stops. The heat dissipates. No explosions, no high-pressure releases of radioactive steam. The reactor simply puts itself to bed. Beyond accidents, there's waste. Thorium molten salt reactors burn fuel far more efficiently, producing a tiny fraction of the waste. And the waste has a much shorter hazardous life, centuries rather than millennia. Some designs can consume long-lived waste from light water reactors, transmuting it into shorter-lived elements, a kind of cosmic recycling. Meltdown-proof safety plus manageable waste is a true revolution, potentially transforming public perception and enabling a nuclear renaissance. Nuclear innovation, molten salt reactor, China engineering, clean energy, mechanical engineers, rocks. We stand at a critical juncture in the story of human civilization. The cosmos has gifted us a planet with a delicate climate, and our actions are pushing it to a breaking point. We need a source of energy as powerful as our ambitions, but as clean as the starlight that reaches us. The revival of the molten salt reactor isn't just an engineering project, it represents a profound opportunity. A potential path to clean, abundant, fundamentally safer nuclear energy. The successful test in China has moved this technology from the history books into the headlines, from a forgotten dream into a tangible possibility. Because these reactors can be small, modular, built in factories, they could be deployed with a speed and scale impossible for traditional plants. They could bring carbon-free power to developing nations, replace aging coal plants, and provide reliable baseload to complement wind and solar. Abundant thorium could democratize energy, freeing nations from volatile geopolitics of oil, gas, even uranium. There are hurdles: new regulatory frameworks, public perception, continued materials research. But the story that began at Oak Ridge has entered a new chapter. This reborn design may not be a silver bullet, but it could be one of our most important tools to build a cleaner, brighter future for everyone on this pale blue dot.